Let's begin. Good afternoon, good evening to everyone. My name is Basvesh and I'm working as a team lead at Decos. PCB reverse engineering is a crucial process in understanding and recreating electronic designs. So, in today's webinar, we will explore ways which enables engineers to replicate designs effectively, enhancing their ability to innovate and improve. Agenda for this webinar would be first, introduction to PCB reverse engineering and its advantages. Then we will look at CAD software which we'll be using during the webinar and moving forward to reverse engineering of schematic and PCB layout with actual flow of steps on how it's done shown in a demo. So, what is reverse engineering? Reverse engineering is a process of analyzing, interpreting, and recreating the design out of an actual product. By performing reverse engineering, we can create design file with exact same function characteristics from a finished product. Hence, it's also known as cloning or replication. This process aids in sustaining a legacy active product with no design file available or when there is a need for a replacement of an obsolete component. Reverse engineering can be valuable for product maintenance, improvement, or replication without access to the original design files. Now, I have a poll question for you. It should be displayed on your screen now. The question for the poll is which which process is better approach in terms of effort, time, and cost? Is it A, reverse engineering, or B, redesigning? Please take a moment to answer. All right. Looks like most of you went with an option A, that is reverse engineering. Yes, it is reverse engineering which helps conserve on most important components of any project, that is effort, time, and monetary value. Let's look at how when we discuss the advantages of reverse engineering. Reverse engineering allows to create exact replica of existing design with similar form and fit. All performance characteristics like delay, impedance, crosstalk, etc. can easily be duplicated as original. Cost and time invested for various testings like performance testing, system level testing, and other testing can be saved. And need for recertifying the design like ULC, etc. are not necessary as we'll be recreating an exact replica with no modifications. By performing reverse engineering, design can be analyzed and upgraded to produce enhanced functionality or performance of a product. It helps in maintaining and repairing legacy or obsolete components in the design to sustain the active product. Another advantage is that it benefits us to understand the product position in the market and understand competitor strengths and weaknesses to discover the growth opportunities. Today, to perform reverse engineering, we'll be using the following tools. First is the AutoCAD for conversion of PDF schematic to 2D version of it, and followed by Altium Designer for creation of schematic PCB layout and to do Gerber comparison. As you might have already guessed, PCB reverse engineering follows bottom-up approach rather than top-down, where a CAD design files are prepared from a Gerber data. Today, we'll be looking at reverse engineering of schematic when only PDF is available, and for reverse engineering of PCB layout, we'll be discussing on two different scenarios. In scenario 1, we will have PDF schematic, BOM, Gerber, and PCB ASCII file available with us. In scenario 2, we will have schematic PDF, BOM, Gerber, but the PCB ASCII file will be missing. At first, let us understand the step followed for reverse engineering of schematic on a top level. Now we have a schematic available with us, but only in PDF format. To convert the PDF schematic to a CAD design format, we'll import the old schematic PDF into AutoCAD to convert it into a 2D format. That 2D format can easily be exported from AutoCAD in DXF format. We can easily import the DXF to Altium with straightforward options, which we will be seeing during the demo. Next step in creation of schematic design file is to create the library for all the components. To match the existing design of components, we can copy both the size and the pin locations of the import from the imported DXF. Once the symbol for all the components are created, they will be placed and wired in the schematic. We will look at the demo for schematic reverse engineering along with the scenario 1 of PCB layout reverse engineering. For reverse engineering of layout, we will look at scenario 1 at first, in which we have the schematics, Gerber, drill data, pick and place, BOM, and ASCII file available with us. The missing files are PCB files, schematic library file, and the design or the project file, which consists of all these things. This scenario of PCB layout reverse engineering is the easiest way to recreate the PCB layout with straightforward steps. We will import the old ASCII file to Altium using import wizard option, and Altium will create the PCB from it. Only thing we need to perform after that is to compare the Altium generated PCB with the old Gerbers to spot and fix the differences found. PCB library can easily be generated with one click of an option to extract it from the ASCII generated PCB. Here are a few cautions which we have to consider while following scenario 1 of PCB reverse engineering. After the ASCII file is imported, all the rules and power plane connections won't be accurate. Thus, Gerber comparison and PCB update is recommended. The netlist comparison is required once schematic is created. The netlist of schematic and PCB has to be done before you perform the ECO update from schematic to PCB. Now let's look at the demo of reverse engineering in scenario 1 for PCB layout and schematic reverse engineering. At first, go to File, go to Import Wizard. Once you click Next, you can notice a list of options which we can import it into Altium. You can import from various design CAD tools, that is Allegro, CADStar, Eagle, Mentor Graphics, all of them which are listed here. Right now, the ASCII file which is available with us is extracted from paths, and that is the reason I'm choosing paths ASCII design and library files. Click Next, and we need to add the ASCII file which is available with us. Navigate to the path where you have ASCII file available with you and select the ASCII file. Notice the extension of the file is .asc. Once you have selected the ASCII file, proceed further, and it will ask if you have the library files available as well. If you don't have the library files, you can skip or ignore and proceed further. All right. Once you proceed further, the Altium will automatically map all the layers present in paths to the Altium. On the left side, you can see the layer names listed in the which were used in the patch software, and on the right side you can see the layer names which will be getting mapped in Altium. So for all the signal layers, it will almost match exactly, but for rest of the things it will be different. Like for signal layers, top will be top layer, power plane will be internal, again internal, bottom will be bottom. So the signal layers are easy to navigate and verify, and for rest of the things, for this example, still screen top is will be top overlay in Altium, and paste mask top will be top paste in Altium. This way you make sure you verify all the layer mappings which are happening currently. All the layers which are getting imported will be mapped, and you can verify those, and if required you can modify using the drop down menu. Once you have verified, proceed further, and it will ask if you want to log any errors or warnings. If required, enable. If not, uncheck these options and proceed further. It will also ask if you want to import the clearance rules, routing rules, and high speed rules. Yes, it is. They are required to be imported, so we will be checking those things and we will be proceeding further. As you can see, Altium is automatically creating a new project file under which it will be creating a PCB file which is getting extracted from the ASCII file. Proceed further, and it will start the migration process for us. The timing for the migration depends on the complexity of the PCB. The more number of components, more number of layers, the more amount of time it would take for the migration to happen. That's it. Altium has created the PCB file for us from the ASCII file. First, go to Tools, Polygon Pose, and report all the polygons. And now we have an exact replica of the PCB which we generated from the ASCII file. Next step is to do the Gerber comparison just to make sure that it matches with the old Gerbers. So what we will be doing next will be extracting the Gerbers from the ASCII generated PCB and we'll be comparing it with the old Gerbers. I've already extracted the Gerbers of this PCB, ASCII generated PCB, and I've added it in a CAM document over here. So in this CAM document, I have imported all the old Gerbers which are colored in red, and I have imported all the new Gerbers, that is the ASCII generated PCB, Altium PCB in yellow color. You can modify these colors just by clicking on the color and it will list out all the color options available in Altium, and based on your requirement, you can choose any color required. So to do the Gerber comparison, we'll be enabling two different layers of old Gerber and the new PCB file. Right now, let us do the Gerber comparison for top layer. I have enabled the top of the old Gerber and I have enabled the top of the new PCB. And both the layers are placed on top of each other, and then we can do a visual inspection in this Gerber comparison. As you can notice, we can see few differences present in the design. One is the text size and the font size, and other is the polygon port connect, which is getting connected to this particular pin. So make sure you fix these issues in the ASCII generated PCB in Altium, regenerate the Gerber, and perform the Gerber comparison again and until you match the old Gerbers and the new Gerbers. That is how we can get a final PCB from the ASCII file. Now let's look at how we can recreate a schematic from a PDF. To- For that, first we need to go to our AutoCAD, and here we'll be importing the PDF version of the schematic. Go to import and choose PDF, and then navigate to the path where the schematic file is present. So I have this schematic in PDF format and I'll be selecting it. Once you have selected the schematic, it will list out all the pages present in the schematic. At a time, we can only import one page in AutoCAD and convert it into a DXF format or the 2D format. So you have to repeat this process for each and every page present in the schematic. So first, let's select the page one and proceed further. Before you proceed further, make sure that the scale is set at 1 because we want this, the size of this schematic PDF and the actual design in 1:1 format. So click on, once you have make sure that the scale is 1, click OK, and it will import the PDF to AutoCAD. Next, you simply have to change or save this file in a DXF format. How to do that? Just give file save as and choose the format in which you want to save it as. Right now, I'll be selecting the DXF format, and I will navigate to the path where I want this file to be saved. I have already done this for a couple of pages and I have saved the DXF format. Once you have saved the DXF format, come back to Altium and go to the project where you want to import that DXF file. Before you import that DXF file, right click on the project and click on add new to project and select schematic. It will add a new schematic file to the project which you'll be working on. Once the schematic file has been added, to this schematic file, we can import the DXF. So go to File, Import, and click on DXF. Navigate to the path where the DXF file has been saved. Remember, you have to do this for all the schematic pages separately, and you have to export DXF for each and every page. So while importing it, the Altium will ask if you want to import it as a component or as a primitive. Make sure you import it as a primitive and make sure the scale of it is at 1. And if required, you can place it at certain location in the schematic page. If not, you can leave it at 0 cross 0 and you can proceed further. So as you can see, the DXF file has been imported to the s- schematic file, but all these components and wires are just C lines. They are not actual wires, they are not actual components. And another thing which you can notice over here is the template. Right now, the template which is present in the schematic file doesn't match the PDF DXF format. So let us increase the format of the template, the size of the template. Go to design, sheet templates, go to local and choose a bigger size of the template. You can modify the sheet template based on your requirement, or if you have that mentioned in the PDF schematic, you can refer to that and follow the same template in the Altium. So once you have modified the template, we need to recreate the schematic symbols and we need to rewire them. To do that, copy the symbol which you want to recreate or which you want to newly create. Copy the C lines of that respective symbol and again go to project, right click on the project, add new to project and select schematic library. It will add a schematic library to the existing project. Once that is created, you can paste the copied C lines from the DXF PDF. So right now I'm not able to exactly place it at the center of this origin point. So the problem is the grid. Right now on the bottom left, if you can see the grid, it is set at 100 mils. To modify that grid, you can just simply click on G and it will get modified to 50 mils as well as 10 mils. I'm changing it to 10 mils and I'm placing the C lines which I copied from the DXF. Once you have copied the C lines, add pins to this symbol. How to do that? Go to place, select pin and place it at the locations where you want. Make sure you modify the pin numbers and the pin names as per your requirement. Okay. The length of the pins is quite big, so I'll be modifying the pin length from 300 mils to 100 mils. That's it. We have the pins placed at exact same location and we have the body which is similar to the old schematic which we copied from the DXF file. Once you have created the symbol or once you have added pins for this particular component, you can place this symbol by simply clicking on place on the bottom left of this window, and it will navigate that particular newly created component to the schematic page, and there you can place the newly created symbol on top of the existing DXF C lines. Like this, you have to create for each and every component in the schematic, and you have to do the connections between those components. Right now, since all those DXF lines are just C lines or free lines, you will not be able to wire or connect between the components. Only when you have newly created the components and you have replaced or placed them on top of the existing DXF component C lines, then only we'll be able to connect between the pins. So to connect between the pins or to do the wiring, you just have to click on Control W, or you can go as P and then click on wire. So that will enable us to add wires between the pins. As you can notice, we have placed a single wire just for reference, just for the demo purpose. I have added it here. The size, the pin length which we used for creating of the symbol was quite big, so we have to even reduce the pin length to match the existing design and update, and afterwards we'll have enough space to wire between this LED and the resistor. So once you have done this for all the components, we need to delete off all the old C lines present in the schematic page. And how do we do that? Click on the C line, right click on it and give find similar and click OK. It will highlight all the C lines present in that particular schematic page. Click on Control A, that means selecting all the C lines which are highlighted and delete off the old C lines. So you can see that the old C lines which were present around this particular component is gone. Like this, you have to follow this method for each and every random C lines which got imported from the DXF, and you have to delete them off. Right click on the unnecessary lines which you want to remove, click on find similar and give OK. It will highlight all the similar ones in the schematic page and click delete. Same way for circles and text, you have to follow the same method and delete off all of them and keep only the necessary ones, that is the components and the wire connections between them. This is how we can recreate a schematic design exactly matching the PDF version of it. Now, let's look at scenario 2 of PCB layout reverse engineering. In scenario 2 of reverse engineering, we'll have files which were available in scenario 1. Only the missing file will be ASCII file. We'll have files like the schematic file in PDF, the Gerber, the drill data, pick and place, BOM, but the missing file is the main ASCII file of the PCB will be missing, and the PCB and schematic library files will be missing, and the project file which contains all of this will be missing. In this, in scenario 2 of PCB layout reverse engineering, in which the ASCII file is missing, we must follow some additional steps than scenario 1. First, we need to create a new project file in Altium. To that newly created project file, we'll be adding new CAM document as well as new PCB library. To the newly added CAM document, we will import the Gerber and the drill data to the CAM document. Once you have imported the Gerber and the drill data, we should be able to extract the netlist and export the PCB from the CAM document. Once you have the CAM exported PCB, we need to newly create footprints and paste it on top of the existing components which we can see in the CAM exported PCB. And once you have created footprints for all the components and you have placed it on the CAM exported PCB, we can import the pick and place file which is available with us just to make sure that all the component location matches. And once that is done, we can have a final PCB ready with us. On a top level, the process we saw might look easy. Now hold on. Let's look at the property of CAM exported PCB layout before we move to the demo of it. Board, the CAM generated PCB will have tool generated netlist, and the components lines or the outlines, the assembly lines or the cell screen lines, everything will be as free segments, including the paths, and all the pins of the components will be marked as number 1. So let us see what is the solutions for those. The only solution to fix this is to newly create the components and place it on top of the existing one and delete off the old free segments, the C lines or the pins which were free segments earlier. And to fix the tool generated netlist, we need to import the schematic, and that will automatically replace the net names, tool generated net names in the PCB. Let's go to the demo part of PCB layout reverse engineering scenario 2. First, let us create a new project. Here, give project name and the location where you want this project to be saved, and click on create. You can see here that the new PCB project has been created. To this new PCB project, we'll be adding a new CAM document file. Right click on the PCB project and click on add new to project and select CAM document. We also need to add a new PCB library as well. So right click on the project, add new to project and click on PCB library. All right, it has added, right now we have added the CAM document as well as the PCB library to the newly created project. So to this CAM document, let us import the old Gerber files which were available with us. Go to File, Import, and navigate to the path where you have saved the Gerber files. You should be able to see all the Gerbers which we can import into the CAM document. Select all the Gerbers and click on Open. It will automatically detect the units or the format of the Gerbers, and we can give proceed further and import or add them into the CAM document. Once you have added all the Gerbers, we still need to add the drill data. Let us see if we can generate a PCB from just by importing the Gerbers. To do that, go to File, go to Export, and as you can see, Export to PCB option over here is disabled. The reason, we haven't imported the drill data yet and we haven't done the layer mapping yet. Let us do that now. Let us import the drill data first. Go to File, Import, and click on Drill. It will show all the drill files available with us. Select the drill files and click on OK. Again, it will automatically detect the unit and the format. Just give OK. Now we have imported the Gerber, we have imported the drill data. Another next step which we have to do is do the layer settings. Go to Tables, click on Layers. Here you can notice all the drill layers, all the layer types are mentioned as temporary. We need to change those and modify according to the Gerber layer type. This particular layer is drill, so I'll be selecting drill top. And this is bottom mask, so I'll be choosing mask bottom in the drop down list. This is bottom paste, choose paste bottom. Bottom silk, next is bottom silk, I'll be selecting silk bottom. If you are not sure of what this particular layer is, you can simply turn on that document and check on it and come back and add this layer type. If still you aren't sure what that layer is, you can leave it as temporary and proceed further with for rest of the layers. This particular layer is top mask, so I'll be choosing mask top. And this will be paste top. This will be top silk. This is internal layer, so we'll be mentioning as internal. This is internal layer again. I'll be choosing internal. Same goes here as well. And one last internal layer. And then we have bottom layer, which is automatically detected. And then we have top layer, which is automatically detected. This is the panel design, which is done in mechanical layer. So I'll just leave it as temporary. Both of these files are drill layers, so I'll leave it as drill top. Once you have done the layer type for all the layers, we need to add the layer stack order. But make sure you do this layer type, make sure you set the layer type for each and every layers before you proceed further. Once you have done, click on OK, and it will ask you to arrange the stack up in the proper order. So this is layer 2, so I'll be choosing number 2 over here, and this is top layer, which will be number 1. This is bottom, which will be the last layer, so I'll be choosing number 6. This will be layer 5, which is internal layer. Layer 3, which is again an internal layer. And this is layer 4, and internal layer. So you have the layer order or the stack up order defined. Make sure you verify them again before proceeding further. Top will be 1, bottom will be 6, and rest of them will be the internal layers, which you will be mapping according to the order. Once you have done, click on OK. Now, what we did so far is we have imported the Gerbers, we have imported the drill data, we have done the layer type settings, and we have done the layer stack up arrangement settings. So we should be able to extract the netlist from this particular CAM document. To do that, go to Tools, click on Netlist, and click on Extract. You can notice over here in the bottom left corner that the tool is automatically creating the netlist. So once that process is done, the export option of PCB will be enabled, and we can export the PCB out of it. To export the PCB, go to File, export, and click on export to PCB. The Altium will convert the CAM document to a PCB format for us. Again, the conversion timing depends upon the complexity of the PCB, number of components, number of layers, all of those things matter. That's it. The PCB has been created from the CAM document. As discussed earlier, there are few issues in the CAM exported PCB. Let us see what are those. All the component C lines are free C lines. So the outline of this component shouldn't be moved when I try to move it. But right now I can move it since it is a free line. Same goes with paths as well. The particular pin of any component and all the pin numbers of respective component of just one component, you can see that all the pin numbers are marked as number one. And the net list or the net names present for each and every connections is tool generated. Now let us see how we can fix this. First, we need to create the PCB library or we need to create footprints for each and every component. To do that, you don't have to go to data sheet for assembly outline, pin sizes, dimensions and all, pitch dimensions and all. You can simply copy this particular free lines and go to the PCB library and paste it over here. Here, remove the unnecessary C lines which are not required in the footprint and modify the pin numbers in this particular footprint. Only for the pin sequence, you need to refer the data sheet. I'll give it as pin number 2. This will be pin number 3. This even the pin sequence has been updated. Once you have done that, here on this PCB library window, you can notice we can place this particular footprint in the PCB simply by clicking on place, and it will navigate to the PCB file and it will bring that newly created footprint to the PCB. Place it on top of exactly on top of the existing pad or the C lines. Follow this process for all the components which are present in the PCB. Make sure you provide proper or matching reference designators when you're placing the components. The reference designator for this particular component was J1. So let me modify it as J1. Yes. So you'll be creating footprints for each and every components and you'll be replacing or adding them exactly on top of the existing free lines or free paths. Once you have done that, we will delete the old C lines and the paths present in the PCB. Right click on any of the free paths or C lines, right click on it, click on find similar objects, click on same and give OK. It will highlight all the free paths which are present in the PCB. But before you proceed further with this step, make sure you have done the conversion of vias as well, because as you can see this particular pin is a via but it is as a free pad right now. To do that, let's convert this free pad as via. To do that, right click on this particular pad, click on find similar objects. If you are since you know that it is a via and the size of it will be the drill size of it will be similar, click on same on of the whole size and give OK. It will highlight all the pads which have same hole sizes. And next step to convert this free pad, this particular pad, free pad to via is go to tools, click on convert and click on convert selected free pad to vias. So now we have converted that particular free pad as via. All the vias are present in the PCB now. Only after this step, let us select the old or the free pad which we wanted to delete. Right click on that particular pad, click on find similar objects, give OK, and it will select all the pads which are present in the PCB and click on delete. It will take some time since it has to delete all the pins from the PCB. Yes, all the free pins are gone. Only the VRs and the pins of the respect newly created footprint is present in the PCB right now. Same you can follow for all the C lines as well. You can do it layer specific or you can do it combined. I recommend doing layer specific as we want to retain the connections or the coppers which are present in the PCB. So that is how you'll be recreating the PCB from the CAM generated document. What you'll do is you'll import the footprint and delete off the old pads and C lines in the CAM generated PCB, and you'll convert the VRs from the free pads. And once you have completed all this process, we need to import the pick and place file just to make sure that we have placed all the components in exact same location and orientation. First, let us see, just for the demo purpose, I'll be moving this particular connector away from its respective location. Now, let us see what actually will be present inside a pick and place file. So here is a pick and place file. Inside this pick and place file, we can see the unit in which this pick and place file was exported, and we can see the list of components or the designators present and the comments, the layer in which this particular comment has been or this particular component has been placed, the footprint name of it, the XY location of it, the orientation of it. All of this will be present, but we cannot straight away import this text format pick and place file into Altium. To do that, copy this particular pick and place file and rename the extension of it from .txt to .pik. Once you have changed the extension of it, copy the path of it, come back to Altium, go to Tools, Component Placement, and click on Place from File. Navigate to the path where you have created a .pik file and select that particular pick and place file. As you can see, I had placed this particular connector away from its respective location. Once I have imported the pick and place file, it went back to the exact same location as it was earlier. And that is how we can make sure that all the component locations, orientations are exactly matching. The only issue left in this particular PCB is the tool generated or the CAM document generated netlist or the net names. To fix this, you have to recreate the schematic, and that schematic you have to import it into this PCB. That was all about reverse engineering of PCB layout in scenario 2 when we don't have an ASCII file. Before we conclude, I wanted to present the services that my organization offers. At Decos, we understand the importance of responsible product design and sustenance. That's why we are committed to providing comprehensive services for all your design needs and turnkey solutions on schematic capture, PCB layout design, PCB design analysis, as well as DFM. Decos can offer expertise in helping clients develop and test any electronic designs. We also can offer customizable solutions based on client-specific needs and industrial requirements. A skilled team of hardware firmware engineers can help with any new product designs to prototyping and testing and even modification of existing designs. So that is all for today. I hope you liked the content delivered today and I was able to give you a brief insight into PCB reverse engineering. We would be happy to help you with any of your product design, development, prototyping, optimization, and troubleshooting. We use the best and the latest techniques and tools for our work. Please note, a recorded version of this webinar will be available on our website in a week time from now. We will also send you an email with a link of your registered email ID to access this webinar. Thank you for joining. Have a good day.